Hi, everyone. Those of you that are already connected, we're going to start in just a second. I'm going to do a quick PowerPoint at the beginning, and then we're going to get to the fun part where we actually show you a lab in action. Hello, good afternoon, everyone, and good morning to those of you joining from the other side of the world. My name is Patrick Horn. I am coming at you from Zurich, Switzerland. The company MBW is based in Baden, about 30 minutes from here. So today I'm going to try to be quick with a PowerPoint, because we've had way too many of these all these days, and we are lucky enough to have Ned Hawes connected via another video feed from the lab of Qrometric. Qrometric is our long-standing business partner in the UK with tons of experience, so they'll be actually able to show you the instruments in action. So just to get started, why is it so important that we calibrate temperature and humidity sensors? Well, you should all be familiar with this green book called the CMO Guide, published by the World Meteorological Organization, which is a body of the United Nations, and it lays out various expectations towards the quality of the measurements. And basically, calibration is important because it's the only way that you can assure that what you are measuring, actually, that those numbers are true, and that they are traceable, and that you can share them, and that they are comparable across the world. So I've highlighted chapter 4, part 4 there, but I won't read that to you now. The instrument that we recommend, which is basically our workhorse, so MBW sells a whole range of products. The 473 is, let's say, our workhorse. It's our portable, transportable dew point mirror, also called the chilled mirror hygrometer, and basically works as a reference measurement instrument for humidity and temperature measurements. The main advantage of this instrument is that it's highly adaptable to whatever climate chamber or humidity generator you might already have. So it's a wonderful way to upgrade what you have and add a highly accurate, traceable measurement to your lab. One of the key features is that the mount, so the head of the 473, which is mounted at the end of the cable, there's actually 3 different versions of that head, which is again adaptable to whatever it is you're using. And we'll see this more clearly as we go through. So the RP2 and the SH2 are the 2 heads you see on this slide here. And that's basically a close-up of the RP2. It's a round probe, fits into smaller type of humidity generators, such as the Qrometric Hydrogen. The range for it is -20 to +70. That's dew point range. The SH2 can go a little bit farther down, so -30 to 70. Again, you'll see these measuring heads in the video portion with Ned, so I'll just move through these slides quickly. But basically, both of these are interchangeable, so you can have one 473 with 2 different measurement heads and basically adapt to the equipment that you have in your lab. The SH2 head is, for example, very well suited for climatic chambers. It has a fan at the end of it, so it guarantees that there's good circulation of air over the measuring head. So the key feature, as I mentioned, the measuring heads. There you can see another picture there of the 2 heads, the SHX you see at the bottom, and the round RP2 at your top right. Beyond humidity, we can also measure we can also measure temperature. We have a highly stable PT100 temperature probe. It's calibrated in liquid or air, and it's also suitable for use as a transfer standard. That's why we say that with our 473, you can do both humidity and temperature calibration. Here, I spoke briefly about the fan that's mounted at the end of the SH2 measuring head. Basically, it shows you how the air flows through the measuring head to guarantee that your sample measurement is constantly being, let's say, refreshed, and that it's taking a sample fully from the chamber with constantly moving air. A key feature of the 473 maybe some of you don't know this, but actually water doesn't always freeze at 0 degrees, but it always melts at 0 degrees. So to calculate a dew point or a frost point when we're at 0 degrees, the 473 has a key feature where basically we cool the measuring head way below 0 to force the water to freeze, and then we take the temperature back up, and we know that it always melts at 0. So that's a key feature. We call it the force frost function, and basically eliminates the uncertainty. Do we have here frost or is it dew? I mean, dew in the form of supercooled water, which could in essence be below 0. However, we do it the other way around. If we melt ice, it's always going to melt at 0. So that's one of the features that our instrument has. A separate and second piece of equipment that we offer is a T12 thermometer. You see it in the top picture. You can see the T12. It's that gray box with many white cables coming out of it, connected to the climate chamber. At the bottom, you see it also working with the spider. The spider is basically nothing more than a complicated way or fancy way of holding the 12 probes within the climate chamber to make sure you can measure throughout and evenly the chamber. Combined with the 473, it gives you a full system to do a full climate chamber validation. All of this can be controlled from the Gecko software, which we sell, which we give free of charge with all of our instruments, and allows also for the recording of all the data that you collect. Here I'm giving you a little bit of a sneak peek of what Ned is going to show you in a minute. Basically, some of the instruments, humidity generators that we work with, and how they can be connected to our instruments. So quickly move through that as we are almost past the 10-minute mark. Just importantly for weather systems, obviously, just wanted to share some information that we are being used as a calibration transfer standard by such manufacturers as Vaisala, Rotronic, E+E, meteorological institutes such as DVD, KNMI, UKMO, FMI, and I can share with you who the full names of those because I don't remember the acronyms myself right now. But basically, we are well known in the manufacturer circle as well, and we are fully able to support you with any sensor from different manufacturers to allow you to perform the on-site calibration. The main savings is that if you would develop this capability in-house with our equipment, is that you are able to do it yourself. You don't have to take those sensors off of your weather stations around the country, send them to Europe or to the United States, spend on shipping, lose the time, wait for them to come back. This allows you to do it all in-house, to have an accurate and traceable calibration capability right in your own organization. So now let me switch over to Ned. So Rachel, if you can make that magic happen, and let's go from Switzerland to the UK and let Ned jump in with the lab portion.
Okay, so what I want to do, we've got several systems shown up, so I will spin you through very quickly what we've got set up, and then I'll go into detail with a couple of more. So we have four systems here. The key thing to note is that when you're calibrating a humidity probe, which is a temperature and humidity probe, you need to generate a value, and you need to then take your instrument under test and compare it to a reference value. And what Patrick was talking about is the reference value that we advocate is the MBW. It works by measuring a dew point and the temperature and then calculating a relative humidity. It's obviously much more accurate than your standard R8 probe, which is why it's used as a reference and a transfer standard to take a calibrated value from. So to show you quickly the four different setups, we have here a 973 instrument with the gas flow is generated from the nitrogen cylinder. It comes into a flow mixer and then gets split into a reference. And then this laser hygrometer is our instrument on the test. So that's quite a sophisticated system. but we do that quite frequently. We take it the whole rig on site to do on-site calibrations at power stations, for example, in the UK. Then we have the Rotronic hydrogen. Inside the Rotronic hydrogen is an Rotronic RH probe. And then on top we have the 473 that Patrick was talking about with the RP2 probe through the door of the hydrogen. I'm going to come back to this one and show you a little bit more detail shortly. We then have a very similar system, except this time this is the generator is the Fensor HG101. Probes go through the into the body of the chamber, and the 473 of SH2 is sampling out the gas from the back of the side of the instrument and then back in. So again, you've got your instruments under test into a generated condition and compared a reference value to what you're seeing on the probes under test. And then lastly, we have what's used at the national standard level, which is a Thunder. I haven't got it turned on right now because it's quite low. So you probably wouldn't hear me talk about it turned on. It uses a compressed air supply and a two pressure system into a chamber here. And then we have within the body, we have here temperature probes and a humidity generating body, and then we sample out the humidity gas into this external MBW, which is at 5 seconds. I'm going to focus on the 473 systems and talk you through exactly how they're set up and how they work. Starting with the hydrogen. So ultimately, what we have here is a condition. We can generate whatever set point we want. So at the moment, I've got it set on 23 degrees and 60%. Now that's what this generator is generating. This instrument under test here, which is coming through this is a probe through the door into a chamber here, which I shall show you in a minute. The instrument under test is reading 59.5% RH and 22.94 degrees. Obviously, each of the numbers is different. So we then have what the MBW is reading via the RP2 head. So the RP2 head is reading. So just to compare the two, I don't know if Jonathan can come in and see. We've got 59.54 plays 59.32 on a generated value of 60. Now, the number that we want to compare is this number against this number. This is your reference number. This is your calibrated, traceable to national standards number, as opposed to the number on the generator on the hydrogen itself down here, which is just for indication only. So what you will do is you'll set yourself a series of set points. Now within the hydrogen itself, you can set up a profile. So we can set up a series of temperature and humidity points for it to run through. And we can use the log function on the instrument under test. And then if we go move over to the Gecko software that Patrick talked about, we then have the MBW software, which is then logging the values that the MBW is recording. Then over a period, you will compare the two values. You'll have your reference value from the MBW. You then have your instrument under test value, and you compare the two. Now, within that system, there's a degree of uncertainty. So it's how good is that number? How accurate is that number? How good is this number? What's the condition in the chamber? Are they all? Is it a uniform chamber? The fact is that these two probes are like 5 centimeters apart. Is the difference in the condition okay, consistent over 5 centimeters? All of these combine to create uncertainty. Now, what you will find is with using a chill mirror as an external reference, your uncertainties of calibration are considerably lower than were you just to use a standard RH point. And that's the key thing. It's about creating a low uncertainty of calibration within such an environment. So we generate our various different values. We run through them. Now, what you will see here, so we are currently at 23 degrees, 60%. What you see here on the MBW is 23.07 and 49.48%. How this is working is you will see here, there's a dew point that it is measuring. Now that is actually a temperature. It's the temperature at which the dual frost film will form on a particular surface. Think like you have doing your bathroom, you have a shower, dew will form on your mirror when you turn the shower on, because it suddenly gets very humid in the shower. The humidity condition is a dew point that is above the temperature of the mirror, so it's a dew point of the mirror, which is how these mirrors work. So let me just take the electronic chamber apart and show you inside. So what we have here, this will start, the values here will work. So what you have here, you have a mirror surface there, which is lit by a diode and detected by a photodiode, and it's detecting the point at which a dew or frost film will form on that mirror surface, and it will measure the temperature at that forms, and that will be the dew point of the condition that it's measuring. Now, within the hydrogen itself, the actual condition is controlled by that RH point, so it's not controlled by a very particularly accurate device, but it's measured by the RP2 head, which is. So we're comparing what this value, what this instrument under test is reading compared to this. If I put this back in, and notice what Patrick said, the airflow is basically coming from the air forms around the chamber and goes across the mirror surface here. So if we go that, now you'll notice it's all gone all unstable because I opened the door. That will then start coming back into, that will now restabilize itself. But notice here, it's measuring a dew point and it's measuring the temperature. There's two temperatures here. Those two temperatures are used to calculate the relative humidity. So these are very nice, accurate numbers. From that, you can get a very, very good number for the RH, and it's that which you compare against what the instrument under test will do. Okay, but very similarly, we have here with the Fensel system. These are your instruments under test. These are into a little. So that's your this is a meteorological probe that's going into a chamber. If you want to see, there's a little box chamber inside there, and the humid air flows back and around that way. So you've got two instruments under test here. There's a they're both Varysian here, and again just to show you the difference here. So this is the SH2, which is sampling out of the back. The side of the chamber. And what happens, just to show you the top of the mirror. The gas comes through and over the mirror. So you see the shiny mirror surface, it comes over that, is sucked through by a fan and then recirculated. And then what we have here is an optical module with a photodiode and an LED. So that's shining light onto the mirror and detecting the temperature at which, detecting the point at which the dew or frost film forms, and then measuring the temperature, which is what the dew point is. So, and notice what happens is when I press dew frost control on this, that's then controlling the temperature of the mirror to the point at which the dew or frost film forms. So I'll turn that on now, and that will then take the temperature down. It comes to a point where it becomes a stable layer on the mirror surface. And it's at that point that we have a real value. So that's a stable dew or frost film on the mirror because the temperature is being controlled to the point at which the dew point of the condition. So if I want to change value on this, on the frontal, you change value on this dial here. So if I want to knock that down to, let's say, 25% RH, this chamber here doesn't control temperature. The hydrogen is a more sophisticated chamber that controls temperature. This is just an RH. You have to control the temperature yourself. So, but just to take it down from 65%, so let's say 25%. So it's quite quick. We then move back, so that will then stabilize on there, and then you'll see that the condition is changing quite rapidly on the mirror. It will then find the point at which the geofrost point is, which is, again, we've gone down from 15 degrees to 3 degrees here. And it will come, but notice that the number that we want to compare is 25 degrees. Notice it's quite a big difference. So the reference value is the number that we want to take compared to the change value. To do the same thing on the hydrogen, if I want to change the condition here, we change from 60% to 10%. Again, I can do this with, we can change the temperature on the hydrogen. The temperature will go between 0 and 60 degrees, and 5 and 95% is standard. They can exchange. And the frontal will go from 2 to 99% RH, controlled. And the thunder, the big one, that goes to from -10 to +70 degrees. 10 to 95%. So you can see now on the as the hydrogen changes condition here on the RH, and it's coming down. You'll see on the gecko that's logging that difference. And on the instrument and the test, should be changing too. How are we doing, guys? Is that that's kind of my 10 minutes. If that is sufficient, if anyone has any questions or anything, I'll be happy to answer them.
Okay, so yeah, we can go to Q&A. Thank you very much, Ned. Did you want to sort of stay on with your video just in case Patrick wants to direct any questions at you? And Patrick, if you turn on your video and microphone.
Yep, I'm coming back. Okay.
So I think Patrick's already answered a couple of questions. If you look at the Q&A section, we do have one more from Narayana. I think it's, have you or are you trying any other liquid to know temperature except mercury and alcohol?
Did you hear that?
Are you trying any other liquid apart from mercury and alcohol for temperature?
For temperature measurements, we work in Celsius. Mercury thermometers would be considered obsolete these days. They're not particularly accurate to make good measurements.
I think your audio broke up a little bit there.
I would just say mercury thermometers are rather obsolete now. Not something that we would consider. Most of the thermometers that we use are platinum resistance thermometers, which change their electrical resistance depending on temperature, and measure the resistance and calculate the temperature. That's how all the temperature measurements and all of these instruments work. You can convert to a mercury unit, but it would be quite unusual in this day and age.
Okay. Do we have any more questions from the audience? Not that I can see.
Patrick, is there anything that you think I should I should add to that. I was kind of
No, I mean, you try to do in 10 minutes what normally we do in half a day when we visit a customer. So I think you did a great job summarizing and showing everything. So thank you for joining us, Ned, and for your help. And thank you for sharing your lab with us.
Okay, no worries. All right, well, I shall sign off.
Thanks again, Ned, for your time.
Okay, Patrick, did you want to provide any more details or go through any more slides in a bit more detail? We've got a couple of minutes left. Can't see any questions coming through, so you obviously all did a great job, and it's all very clear and simple to understand.
Yeah, well, no, I mean, we wanted to keep the PowerPoint relatively simple and then show more of the lab. So I think we were able to do that. If anybody has any more questions, there's tons of information I can share, but you know, we only have a minute left, so I'm not going to attempt to enter any more details at this time. But do feel free to contact me. I have my virtual booth in the exhibitor lounge. I'm also hanging out in the attendees lounge as well. So feel free to come up and ask any questions or send me a meeting request, and I'm more than happy to dive into any more details, send through any data sheets or information, or just theoretical questions you might have about the theory behind all these things. I've only been at the company for 2 years, but I've learned quite a bit in this time, and also looking for business opportunities in India. So if you're a distributor or an agent and you see some opportunities, please talk to us. We're always trying to grow. We are in the process of developing the market. So happy to hear from you.